So in this tutorial we're going to look at combined probabilities, which is what you have to deal with when you have more than one thing happening. So two trials, if you like. Remember, a trial is an experiment, a probability experiment. And ways you might approach this are, well, you might use a tree diagram. Okay, you don't have to use a tree diagram, but it sometimes is a good idea, remembering that on each set of branches the total probability must be 1. You're going to need to make a decision if two things are happening and it involves picking things out of a bag or a hat or a chocolate box or something. You need to decide whether the items are replaced. So is the first thing replaced before the second thing gets taken out? And if they're not replaced, remember that the numbers, particularly on the bottom of the fractions, go down by 1. We'll have a look at one of those in a minute. Whether you use a tree diagram or not, it's always a good idea to write down the probability you want with and or between the things, okay, as you would naturally say it. And then once you've done that, and is always times and or is always plus. Just pausing to note that the and rule, and is times, works for independent events. In other words, the first thing doesn't affect the second thing. And the or rule works for mutually exclusive events, which means the two things can't happen at the same time, like a head and a tail on a coin. They are mutually exclusive events. And there is a trick you can use, a couple of tricks here. It's often quicker and easier to use. Well, if you want to find the probability that something doesn't happen, so the probability of not A, it's often easier to find the probability that it does happen and subtract it from 1. And similarly, if you want to find the probability that you get at least one of something, find the probability that you'd get none of that something and subtract that from 1. And often the question will highlight a word which tells you to use that trick. So anyway, let's apply this to some questions. So here we have the box of chocolates with 8 dark chocolates and 4 milk chocolates in it. So that's 12 in total. And 2 chocolates are taken at random. Now, it very clearly says they're both taken out at the same time, but we treat that as one after the other without replacement. So these are clearly not replaced. In my experience, in my household, chocolates are never replaced. And we're asked what the probability is that they are different types. Well, we don't need a tree diagram necessarily, but we are going to draw one just to show you how they work. So, first chocolate can be dark or milk, and we put the probabilities on the branches. So the probability of a dark chocolate is 8 out of 12, and because there are 8 dark chocolates and 12 chocolates in total. And then the probability of a milk chocolate is 4 out of 12 for the similar reasons. And just note that, of course, those two things do add up to 1. And then we need to put a second set of branches on, okay, after each choice here. So if it's dark first, it can either be dark or milk second. And if it's milk first, it can still also be dark or milk second. And now, because we're without replacement, we need to be careful with the probabilities. So how many dark chocolates are left if we've already taken a dark chocolate out? Well, the answer to that is 7. But how many chocolates are left? Well, that's 11. And that's what I mean by the numbers going down by 1. The number on the bottom always goes down by 1 when it's not replacing, when we're not using replacement. And depending on which one you're taking, the number on the top might go down by 1 as well. Now, what about milk chocolates? Well, there are still 4 milk chocolates left and 11 chocolates in total. And again, check that those two add up to 1. For the second set of branches, well, there are 8 dark chocolates left, but only 11 chocolates in total. And now there are only 3 milk chocolates left if I've taken one out, and 11 in total. And again, the numbers are going down by 1. Now, whether or not we've drawn that tree diagram, we should now write down the probability with ands and ors. It's perfectly okay to use D and M for dark and milk. So, what's the probability they are different? Well, it's D and M, or M and D. Now, if you think those two things are the same thing, just have a look at the tree diagram. There are clearly 2 routes through the tree diagram, and you can see there are 2 ways of getting different chocolates. So although you end up with one of each, you've got them in a different order. So let's now do the probabilities. So the probability of a dark chocolate, according to my tree diagram, is 8/12 and is times, and then following that first root through, I get 4/11 there. So that's that root there, and we're multiplying because it's and. It then says or, so we add, and then we follow this route through the tree diagram. As I say, you may be able to do that in your head without a tree diagram, but it's 4/12 for the milk chocolate, and then 8/11 for the dark chocolate. And if you do all of that, which you could do in your head if you like, that is 32 132ths plus 32 132ths, they turn out to be the same thing, which is 64 132ths, and that does in fact simplify to 16 out of 33. So there we go. There's an example of a combined probability question. Let's have a look at a slightly different one. Here we have a biased coin landing on heads 70% of the time. So the probability of a head is 0.7, and therefore the probability of a tail, of course, is 0.3, is it not? So let's actually just write that down. So probability of head equals 0.7, and the probability of a tail, which is in fact you could call not head, head dashed, h dashed, is 0.3. Okay, now notice that there's a highlighted bit in the actual question. John tosses the coin 3 times. What is the probability that he tosses at least one head? And I think that's the question telling me to use this trick here. You could do it the other way, but it would take you a lot longer. So we're asked about the probability of at least one head, and I'm going to use the trick. It's 1 minus the probability of no heads. And so that's 1 minus the probability of tail, and tail, and tail. Now, I can just do my and or thing here. Actually, there are no ors, so it's just ands, and I get 1 minus 0.3 times 0.3 times 0.3. And if I do that, I get 1 minus 0.027, which is 0.973. Okay, so it's very likely I will get at least one head, which you would expect because, of course, it's biased towards heads. But there we go. I've used the trick at the bottom of the blue box there.